A single spark of electrostatic discharge, or ESD, carries enough concentrated voltage to instantly fracture nanoscale silicon and short-circuit a modern processor. In today's hardware environment, AI processors and high-speed interconnects handle massive data rates on progressively smaller architectures. As the internal geometry of these chips shrinks, their tolerance for stray electrical interference drops to zero. To keep these systems alive, we have to construct an electromagnetic shield. We do this by calculating exact electrical parameters and placing specific protection components on our high-speed and industrial interfaces. Skipping component-level protection guarantees that an expensive, fully functional circuit board will fail the moment a user touches a port or a nearby motor switches on. Selecting a protection device relies entirely on three quantitative rules. Step 1 is matching the working voltage, or VRWM. The ESD device's voltage rating must be equal to or slightly greater than the circuit's normal operating voltage. If the rating is lower than the line voltage, the protection device will constantly leak current and drain the system's power. Step 2 covers clamping voltage and peak pulse current, VC and IPP. When a surge hits, the device clamps the voltage down. This clamped voltage must be lower than the maximum limit your chip can physically survive. The peak current rating you select depends entirely on whether your product lives in a static-controlled office or an outdoor environment exposed to lightning. Step 3 is parasitic capacitance, or CJ. This diagram compares two digital eye diagrams, which engineers use to measure signal quality. The left side shows a closed, distorted signal. The right side shows an open, perfect signal eye, achieved by selecting a protection device with an ultra-low capacitance of 0.14 picofarads. Looking at this capacitance limits guide, you can see the strict cutoff lines for system bandwidth. PCIe Gen 6 and USB 3.2 require less than 0.3 picofarads. HDMI 2.1 needs less than 0.5. Gigabit Ethernet can tolerate up to 4 picofarads. Placing a high capacitance component on a fast data line acts as a low-pass filter, physically absorbing and destroying the data packets. You can successfully block a static shock, but if your capacitance is too high, you will permanently sever your own device's ability to communicate. We can test these rules against the USB 3.1 Type-C interface. It pushes 10 gigabits per second of high-speed data right next to 100 watts of high-voltage power. This schematic breaks down a USB 3.1 Type-C port. The super-speed TX and RX differential pairs transmit data at massive speeds, making them extremely sensitive to any signal degradation. To protect these pathways, we attach bidirectional ESD diodes, featuring an ultra-low capacitance of 0.14 picofarads. This intercepts static strikes while leaving the 10 gigabit signal perfectly intact. The legacy D+ and D- pins max out at 480 megabits per second. Because the speed is lower, we can consolidate our parts and use a 4-channel integrated ESD array with a slightly higher capacitance limit of 1.0 picofarad. The V-bus power pins present a totally different environment, carrying up to 20 volts and 5 amps. We assign a heavy-duty transient steering suppressor, or a TVS diode, rated for at least 22 volts to handle the high electrical potential. If you apply the same low-voltage 5-volt ESD chips used on the data lines directly to the 20-volt V-bus line, the normal operating current will overload the chips and cause immediate thermal destruction. Modern high-density interfaces demand a hybrid approach. You must treat power pathways and high-speed data pathways as entirely separate engineering problems. Stepping away from computer internals, industrial factory floors rely on rugged communication lines like RS-485 and CAN buses. These industrial buses operate at low speeds, usually well under 1 megabit per second. This means their data lines are highly tolerant to capacitance, allowing values anywhere from 30 to 100 picofarads. The true threat here is raw energy. Massive electrical surges, lightning induction, and switching transients from nearby heavy machinery will easily vaporize standard ESD diodes. This schematic illustrates a two-stage protection architecture. A primary component, like a gas discharge tube or a thyristor surge suppressor, absorbs the thousands of watts from the incoming surge. A secondary ESD diode then clamps the remaining residual voltage down to a safe level for the processor. Industrial protection flips the priority list. You sacrifice ultra-low capacitance to gain absolute brute force energy absorption. Having the perfect components on your bill of materials means nothing if your physical printed circuit board layout is flawed. Looking at this 3D layout, the ESD devices are placed immediately adjacent to the interface connector. You must intercept the energy at the edge of the board before it can travel deeper into your circuitry. When routing multiple differential pairs, utilizing multi-channel integrated ESD arrays reduces your total component count and simplifies the trace routing. This close-up highlights a massive copper pore connected to the ground pins. You have to provide the lowest possible impedance path for the surge to escape directly to ground. Proper physical routing is the foundation of the shield. Without a wide, low-impedance escape route, the static energy will simply bypass your protection diodes and find a path through your core processor. These completed schematics prove that you can defend both the most sensitive high-speed lines and the most brutal industrial environments. By matching parasitic capacitance to your data rates, verifying working voltages, and building multi-stage surge barriers, you control exactly where rogue electrical energy flows. Check the video description below to download our free Capacitance Limits Quick Reference Guide PDF to keep on hand for your next board layout. Applying these quantitative rules entirely eliminates the threat of unpredictable static failures and turns vulnerable silicon into robust field-ready hardware.